Hello everyone, welcome to the week 12 lecture on the grid generation techniques for the course Introduction to CFD. So in today's tutorial session, mainly we will be studying what are the different grid generation techniques so that we can efficiently solve the CFD problem which we have in our hand. So that will be the main focus of today's tutorials. So I am Sumant Marak. I am a PhD research scholar in Department of Mechanical Engineering at Indian Institute of Technology, Bombay. So coming to this week's content, which you can see in the slides, this was mainly based on the grid generation for computational fluid dynamics. And first, we had seen what are the different types of grids which can be generated wherein we can solve the problem. So we mainly saw that there are two categories of grids. One is the structured and the other is the unstructured grid. And then we went on to see mainly how we can generate the structured grid and what are the different possibilities within a structured grid, and two main methods in which we can kind of generate the structured grid, which is algebraic method and the partial differential equation method. So once we were able to generate the grid, we considered a small Poisson equation or a steady state heat conduction equation, and then saw how we can kind of convert these governing equations into this body fitted grid, and then how we can solve the governing equations in the transformed plane. So that was about the transformation of equations. Finally, we also saw what are the issues with the structured mesh, especially for complex geometry problems. And then we went on to see what are the possible methods for unstructured grid generation. So as I said just now, so we can mainly classify the grids into two types, structured mesh and the unstructured mesh. So we have to kind of differentiate properly between the structured mesh and unstructured mesh. So usually whenever there are fixed number of lines like which are meeting at say a particular grid point or an intersection, so in the whole domain you divide the domain in such a way that there are fixed number of lines which are meeting at any given point. Okay, so in that case such a division of domain is called a structured mesh. So just to give an example, for example, I have a rectangular domain. Assume that this is a channel flow problem and this is my domain. Now I divide the domain in such a way that whatever points I take in this particular domain, the intersection points, if you see this intersection point, there are mainly two lines which are meeting at this intersection point. Okay, if you take any other point in this domain intersection point, there are two lines which are meeting at this particular point. So this can be classified as a structured grid. You can have more complicated case also wherein structured grid format can be followed. Okay, but when we go to unstructured grids, what we mainly observe is that at a given grid point we can have intersection of any number of lines. So in 2D case we saw that there were only two lines which are intersecting at this grid point for a structured grid. Similarly, in three-dimensional flow, we will have three lines which will be intersecting at a point, and that will be fixed throughout the domain. Throughout the domain, three lines will be intersecting for a 3D flow. Okay, so that mainly constitutes our structured grid. Okay, now when we come to unstructured grids, okay, I can have one grid point, for example this grid point P, wherein, okay, how many lines are intersecting? 1, 2 and 3 lines are intersecting. Okay, So now in the neighbor I can have another grid point L. Okay, here if you see only two lines are intersecting. So the number of lines which are intersecting at this point and this point is mainly different, and such a division of domain, I would say, can be classified as an unstructured grid. Okay, so this is the basic meaning. So I hope that this definition is very much clear, because this is very important. Many a times, usually in a crude way, what people tell is that if we have like quadrilateral cells arbitrary, this kind of form something like a structured mesh, and say if we have triangular elements, then these make up an unstructured mesh, but that is not completely true. Okay, you can have a domain in which you will have triangular elements, but even then the mesh will be structured. Okay, you can have such a case. So for example, which I am just showing here, so again it's a channel kind of thing, it's like a curved channel you can say. So here if you see at every grid points you have like intersection of equal number of points, equal number of lines, sorry. Okay, so in even with kind of triangular elements you can have structured meshes. Okay, but mostly the combination of a quadrilateral and a triangular element in a domain, usually this kind of leads to an unstructured mesh. Okay, so in that way also we can try to gauge whether it is a structured or an unstructured mesh, but the perfect way would be to see how many lines are particularly intersecting at a particular grid point. Now, after looking at the definition of a structured and unstructured grid, which is indicated in this slide also, we saw that when we have a very complex geometry, we see that these structured meshes become very much skewed in nature, and they might lead to unphysical results, or else oscillating results which kind of diverge after some time. So in the class material also one example was given for this, but let me take a slightly different example. So consider that I want to do simulation of simple flow in a tube basically. Okay, so the cross section will look like something like this, which is circular in nature. Okay, now I want to fit a grid from this rectangle. Okay, I want to map this into this particular domain. Now how do you generate a mesh using the quadrilateral elements here? So what will happen is that in a way you can generate it, there is no issue in generation, but what will happen is that when you generate such kind of mesh, you usually see that at these intersection points, okay, in this intersection point and this intersection, that is basically corners of the domains, you can say, the mesh becomes very much skewed in nature. What we mean by skew here is that the lengths in the adjoining directions are there is a huge difference in them. Okay, so for example you can have a neighboring grid point something which looks something like this. Okay, so basically what we see is that this particular one length of the element, say L1, and if you take the adjoining element length L2, then there is a huge difference between L1 and L2. So that is what is called as mainly the skewness of a mesh. Okay, so we see that these kind of elements, this type of structured grid generation leads to very high skewness. Also, if you see, for example, in this element only, if you see, if you call this as L1 and say the length of the other element as L3, then there is a huge difference between L1 and L3. That is in the same element only. If you take the edge lengths, there is a huge difference. So this also leads to high skewness. So this also is a probable definition of the skewness. Okay. So L3 by L1, if you consider, then the ratio will be very large. Okay. So that is what is called as skewed mesh. So if you want to try to solve these problems with this particular structured grid format, you usually land up by default with these skewed meshes. There are many strategies to avoid this skewness, and one of the main strategy is a multi-block gridding. Okay. Now if we take the same example, okay, we can divide into a certain equal number of domains. Okay, then we can quite easily mesh this particular domain. Okay, so we can take a square here in this particular area and do the normal Cartesian grid generation, and then whatever remaining blocks are there, here smoothly we can generate the grid points without having skewness. Okay, so that is also possible. That is techniques which can be used to come up with so these are the techniques which we can use kind of to come up with a structured grid generation on a complex geometry, and at the same time we can also kind of avoid the necessity for skewness which will happen. Okay, so these were some of the techniques in structured grid generation. Okay, then we wanted to mainly see how we can kind of convert the governing equations which we have in the xy plane to the zeta and eta plane, which is our structured mesh plane. Okay, so basically we use something called as Jacobian transformations, wherein we kind of use say either algebraic technique or a PDE technique. In algebraic technique we use just an analytical expressions. Okay, so to get the y equivalent at this eta zeta plane. Okay, so once we kind of get that, we have to convert our equations like which are present in the x and y. So we have dou u by dou x, dou v by dou y terms. Okay, usually in the governing equations we want to convert that into dou u by dou eta, dou u by dou zeta, something like that. Okay, so for that we use this chain rule, wherein we can write any variable phi, dou phi by dou x, as say first dou phi by dou zeta and dou zeta by dou x, then dou phi by dou eta and dou eta by dou x, because phi will be now in a computational space a function of zeta as well as eta. So basically you can write phi as a function of zeta and eta. So that is why now you have to differentiate it with both zeta and eta. So this is just a chain rule expansion. So using this particular relation, you can convert all the equations, governing equations, into the computational space, that is the zeta and eta framework. Okay, but the main thing which still remains unresolved is how do we actually get the value of d zeta by dx, because zeta eta plane is a simple Cartesian plane. We can directly obtain d phi by d zeta using our finite difference or finite volume method, because it will be just phi 2 minus say phi 1 divided by delta zeta. Okay, so but we cannot find d zeta by dx because xy is a complex geometry plane. We cannot directly get dx value. Okay, so we have to convert this d zeta by dx into something which we know. For example, x zeta, we have to convert it into the form of x zeta. So for that particular thing, we kind of come up with this transformation relations, which we will try to actually derive in one of the tutorial problems today. Okay, so just hang on for a moment. We will try to derive these equations, how these things comes. But using these equations, we can again convert the d zeta by dx, which is denoted by zeta x, in terms of y eta, like for example dy by d eta, which we can easily evaluate, right? So because eta is in the our Cartesian space, which is our computational space also. Okay, so let us start with the some of the tutorial problems. Okay, so the first question, the matrix of transformation zeta x represents which of the following has been asked. So basically all the four options have like ratio of the local radius of curvature of the grid in physical space. Then in the option number B we have ratio of arc length in the physical space to computational space. Then we have ratio of area in computational space to physical space. And we have ratio of arc lengths in computational space to the physical space. But before this we have to understand what really is the physical space and what really is the computational space. Okay, so again let us come to this particular example of flow in a tube. Okay, so for example, if I want to have like for example just a 2D axisymmetric thing. Okay, and say we have a kind of constriction in the tube. Okay, so now this is the physical domain which we have. Okay, so this can be denoted by x comma y. Okay, so this is our xy plane wherein we want to solve the equations. Now we try to convert this xy plane into something as zeta eta, where we get a simple rectangular channel kind of thing, so that we can directly evaluate d zeta by d d phi by d zeta and d phi by d eta. Here we can evaluate those things very easily. Okay, so this particular plane is called as the computational space. Okay, so that is the meaning of physical space and computational space. Okay, now in the question what has been asked is like zeta x, what does it indicate? Okay, zeta x, if you expand it, what you will get is dou zeta by dou x. Okay, now what is dou x in terms of if we see the physical plane? Okay, so if we see the expression for this zeta x, we have dou zeta by dou x. Okay, so if we look at it pictorially, then it becomes say, see if we have a simple curve in one dimensional domain which is in the xy plane, then we convert it to zeta eta plane, and now we are concentrating only on zeta. Okay, so we have zeta naught and then zeta n, in between we have zeta I plus 1. Similarly in the xy plane also we have like xi plus 1, something like that. So what we need here is dou zeta by dou x. So it is nothing but like zeta I plus 1 minus zeta I divided by so delta x. Now if we see what is zeta I plus 1 minus zeta I, it is nothing but our length, arc length in the computational space. Zeta I plus 1 minus zeta I, if you look into this image, you will easily understand that it is nothing but the length of one particular segment of arc in our computational space. Whereas if you see delta x, it is actually arc length in this physical space, the curve length. Okay, so as per the options, option number D has to be correct, because what it says is that ratio of arc lengths in the computational space to that of the physical space. Okay, so if we are able to understand what is physical space and what is computational space very clearly, then we will be able to calculate, answer this question very easily. Okay, so I hope that the meanings of computational space and physical space are quite clear in this structured grid generation method. Okay, so just let us go to the next question. So in the next question, the vorticity expression has been given in the physical space, which we all know very well. Okay, so vorticity is the curl of velocity, and if we take the z component, what it turns out to be is dou v by dou x minus dou u by dou y. That is what it turns out to be if we take the curl and then if we take the z component. Okay, this we already know. So what is being asked in the question is, how do you express this vorticity now in a zeta comma eta plane? Okay, so I had explained about this earlier also. So we use the chain rule to kind of differentiate the things. Okay, so we have dou v by dou x minus dou u by dou y. Okay, so we have to go by individual terms here. First we have to convert this dou v by dou x term. Okay, so what we can write is dou v by dou x, we can write using the chain rule expansion, because v is now a function of zeta comma eta. So I'll write dou v by dou x as dou v by dou zeta, okay, into dou zeta by dou x. Okay, also since v is a function of eta also, so what we kind of write is dou v by dou eta into dou eta by dou x. Okay, I hope that this chain rule expansion is clear. If not, please let me know if you have any queries on the chat box. Okay, so this is the way in which we kind of write dou v by dou x formula. Okay, in the from the physical plane we have mapped it into computational space. Okay, so similarly we have dou u by dou y, so that also we can write in a similar fashion, okay, which I have already written here. So dou u by dou y, again we can write it as dou u by dou zeta into dou zeta by dou y plus dou u by dou eta into dou eta by dou y. I have just used the shorthand notation here. Dou v by dou zeta can be just written as v zeta. Okay, so I hope that you are comfortable with this shorthand notation. Okay, so what is remaining is just to take the difference of these two terms, dou v by dou x and dou u by dou y, and then we will just land up with the expression for vorticity. Okay, so if we kind of take the difference between this dou v by dou x and the dou u by dou y, which we have expanded, so we come up with an expression, and if we try to see the options, which of the options should give the matching answer? Can you write down on the chat box? V zeta and zeta x. V zeta and zeta x, we have it in the third and fourth option, and then v eta and eta x in the positive sign. So yeah, all the terms are also correct. Yeah, so it should be option number C. Okay, it should be option number C. Yeah, option number C should be the correct answer for this question. I hope you have understood how we can kind of convert the equations in the physical space to the computational space, because ultimately when we want to solve these equations, we have to do this exercise, because we might be getting new equations, and whenever we get new equations we have to solve it first on pen and paper, come up with the equations, and then we can start coding. Now you can see that dou v by dou x minus dou u by dou y evaluation on a complex geometry is very difficult. Okay, it can be done, but it is quite difficult exercise. Okay, quite mathematically rigorous exercise, but if you kind of convert this into a computational space, it becomes very easy now, if you see, because we have basically dou v by dou zeta, and we have like dou u by dou zeta, which we can evaluate easily using our central difference scheme or whatever we want, and then we have this zeta x, okay, which we can convert it into x zeta or eta y, whatever is there, using the Jacobian transformation. Okay, so that also then can be evaluated very easily. So this equation can now be solved very easily on our computational space. So that is the main advantage of these conversions. Okay, so now in the question number 3, cell has been shaded in the physical plane. Identify its counterpart in the computational plane. So always we try to map these physical space into the computational space. Okay, so it's just like you have to imagine like an animation kind of thing which is going on. Okay, here now we have a physical space which looks like this. Okay, now just imagine that you are just putting some force on this particular end, and similarly you are putting some force on the right end, so that it will become from this horizontal to perpendicular. Okay, you just push it from both the ends so that this will become like a horizontal, and the other two faces will become vertical. Okay, so it will basically become a channel. From this curved kind of channel it will become a straight channel. Okay, so that is the transformation which we want to do. Okay, now we have the same points here. Okay, like if I mark like 1 2 3 4. Okay, I have the same points 1 2, sorry, 1 2 3 4. And here also if I have like p q r s. Okay, here also I'll be having the same points P, Q, R, S. Similarly on this vertical lines also same thing will happen. Okay, so this is the transformation which we are intending. So in the question it is being asked, okay, we have a kind of shaded region. When we do the transformation, the shaded region will belong to which of the following cells which are indicated by the letters, that is being asked. Can you identify the answer and write down on the chat box? This is actually simple visualization exercise. It doesn't have any much kind of mathematics to do here. Okay, if we kind of see this particular physical space, we have this shaded region mainly I think in the first, second, third, fourth, fifth column, and then we have it in the second row I think. Yeah, so fifth column and second row, if you see 1 2 3 4 5, and then second column. Okay, so the I think the answer should be C, because it corresponds to 1 2 3 4 5 and 1 2. Yeah, so the correct answer is C. So that is what I have written here. So we have totally around like 3 rows and like 8 column points. Okay, that is what I is equal to 1 to 9 it has been written. But I am trying to map the cells here. Okay, cells will be 8 only. Okay, similarly rows also will be 3. Okay, for j is equal to 1 to 4 points. Okay, now the shaded region kind of lies in the second cell in row and the fifth cell in the column. Okay, so that is particularly which comes out to be C here. Okay, so this fourth question is mainly based on your body fitted grid generation, wherein you had two different methods, sorry, two different domains. When you have simply connected domain, uh, doubly connected domain, and then you have multiply connected domains. Okay, so this is one particular example of a doubly connected domain. Okay, so here we want to try to kind of predict the flow over an airfoil, which is particularly important in aerospace industries. Okay, so mainly we try to generate a structured grid around this airfoil by using this doubly connected mesh generation technique. So what we kind of do is here, I'll just explain it through image only. So just assume that instead of this airfoil I have a simple circular cylinder. Okay. Now what I'll try to do is that I'll try to cut this particular extension side apart. So basically what I'll do is that I'll push this in the upward direction, I'll push this line in the downward direction. Okay. Then whatever I have here, I'll make it only as a one line. Okay. So that is the strategy which we use. So mainly this is our particular physical domain of interest. Now we want to convert it into a simple Cartesian domain. Okay. Rectangular domain. So mainly this say I'll call it as whatever it is in the question. Let us take the same thing: B4, B3, B1, B2. B4, B3, B1 and B2. Okay. So when I move this like the B4, what will happen is it will come on the left hand side. If I just push it down and then like take it towards the left side, so B4 will come here. Okay. Then similarly we see that the B3 will go into the right side, and this whole length, which I'll just write as this dash here. Okay. This will be B2. You have to just do an visualization, imagination and visualization here, that when I just pull this to the downward side and push this to the upward side, how can they be made into this simple Cartesian domain. Okay. What will be remaining is the bottom, that is the B1. Okay. So that is how these transformations are made. Okay. So I hope that this is clear. So if we see the transformation, so basically we see that at the bottom we get B1. Okay. When we push this B4 into downward direction and B3 into upward direction. Okay. And then B4 will come on the left side, B3 on the right side, and B2 as it is on the top side. Okay. So now we try to solve this particular problem in this particular physical space. Okay. So that is the main approach which we use in this Jacobian transformations. Okay. So if we see, then what should z be equal to? It will be b1. What will be x be equal to? It will be equal to b2. Okay. So if we see the options, they have asked x, y and z. So basically we have x as b2, similarly y we have it as b3, and z we have it as b1. Okay. So b2, b3 and b1 corresponds to b2, b3 and b1 corresponds to option number b. So that should be the correct answer here. Okay. Now if we come to the fifth question is as follows. So we have two different statements here. Statement 1 says that Jacobian is a ratio of areas in computational space to that of the physical space in 2D. Okay. So basically what they are telling is that Jacobian is a ratio of areas in computational to the physical space. Okay. In the second question, the same thing is repeated. Jacobian is a ratio of volumes in computational space to that of the physical space in 3D. So if we see basically the formulation of Jacobian in 2D, if we see which we will derive it in the next question, it will come out to be 1 upon x zeta y eta minus y zeta x zeta. We will derive this in the next question. Hold on for a moment. So if we see in the computational space, if we take the area as 1, then the corresponding area in the physical space that will become, that can be denoted by this particular x zeta y eta minus y zeta x zeta. Okay. So this is what we have observed. Okay. So based on this we can say that this represents the area in the computational space to the area in the physical space. For a 2D problem. Similarly, we can do the extension in 3D also, although we do not have the mathematical form. A similar extension can be done in 3D, wherein it will become volume in computational space divided by volume in physical space. Okay, so both the statements are true here. Okay, so again question number 6 is similar to the question number 4, but instead of a doubly connected domain, we kind of have a multiply connected domain here. Okay, so again we have to do the same kind of exercise. It's not very much different in the way that we have to push this b4 down and we have to pull this b3 up. Okay, so then if we slightly move this down and bring it to the left, we have on the left boundary we have b4, and when we pull it upwards and kind of bring it to the right hand side, so basically that will become the this right boundary. It will become x. It will be nothing but b3. Okay, so b x is nothing but b3 anyways, and in the top as usual we have a b2. I think this can be kind of very much explained using one type of, I think, a fan which you kind of get, like it's just a hand blown fan. I think you kind of have this round color shape. Okay, you have this kind of shape, the fan. Okay, then when you hold this fan, I think it will become like this. It will become small case. Okay, so you what you are doing is that you will be uh, pulling this to the right hand side and pushing this end to the left hand side. Okay, so that is how it comes out. Okay, then it becomes a small rectangle in a sense, that particular hand blown fan. Okay, so similar thing we have to kind of do for these problems also. So that way we can do the imagination quite easily. Okay, so if we see that way, okay, so other things I have left out. B4, B3 and B2 are clear. Now what is remaining is these all these boundaries. Okay, so now all these boundaries we take it as only one boundary. Okay, in this computational space, but since we have to implement the boundary condition, we will have to define the segments. Okay, so first we will get this is pretty easy because we are going from the left hand side. So b4 is adjoining with this b7. So first we will get b7 near the b4 side. Okay, then we will have b5, then we will have b1. Okay, then we will have b6. Okay, which can be told as z, and finally we have b8. B8 is adjoining to B3. Okay, so W will be B8, which is adjoining to the B3, that is the X. Okay, so I have just represented that particular thing here. So mainly if we see this, see the options, they have asked for W, X, Y and Z. So W will be B8, and if we see there is only one option I think which starts with B8. Okay, so even if the options were not there, you should be able to guess the answers. Okay, wait a minute. This is B4 on the left hand side. But B8, B6. Achha, this should be B6 by the way. Sorry for that. Z should be B6 because before B8 you have B6. Okay, B6 you have, before that you have B1. Okay, correct. This should be B6. So Z should be B6. W anyway is B8. Okay, W, X, Y, Z, right? B8 and then B3, B8, B3, then you have Y as B5 and Z as B6. Yeah, so this option number A should be correct option. Okay, I hope that this is clear now. It's mostly of to do with the imagination, and based on your imagination you can hit a diagram on the paper and then mainly map these boundaries. Okay, so that is the approach which is usually followed. Now in the seventh question, as I said, this is more to do with the derivation of the Jacobian. Okay, so here they have asked us to write down the expression for Jacobian. Okay, now we will try to derive this. Okay, so using the chain rule we had observed this relation will hold true. because we had, I think, the way in which this came up, as far as I remember, is like we wrote d zeta is equal to d zeta by dx, okay, into dx plus d zeta by dy to dy, okay. Then similarly d eta we wrote, okay. Then we formed a matrix of d zeta d eta, okay. Then the reverse relation which we wrote for dx sorry dx is equal to dx by d zeta into d zeta plus dx by d eta into d eta. Okay, so we formed another kind of matrix relation with this particular thing, and in this whatever dx dy we were getting, I think we substituted this particular relation. That is how we got this particular relation. That is, this particular matrix is equal to the inverse of this matrix. So basically what we had seen was that this particular matrix A, and this, if you see it as B, then A into B is equal to I was observed. So A is equal to B inverse. So that is how we come up with this particular relation. So once we have come up with this relation, we can easily find what is J. Okay, so if we kind of express zeta x in terms of J into y eta, we can calculate what is J. Okay, so we'll try to do that. So first you have to be able to calculate the inverse. Okay, for 2 by 2 matrix, there is a very small shortcut which you can use. Okay, so usually the determinant, the inverse is given by 1 upon determinant of this matrix into this cofactor matrix, whatever is there. Okay, so but for a 2D case, for a 2 cross 2 matrix, you can use a very short trick. Determinant anyway will be x zeta into y eta minus y zeta into x zeta. It is the difference between the cross product of the elements here. So that is the arrow direction which I have indicated, x zeta into y eta minus y zeta into x zeta. So that will be determinant, and that will come in the denominator, 1 upon determinant A. Then we can do this cofactor by just simple exchange of variables. Okay, for a 2 cross 2 only this is applicable. What we can do is that we can change the location of these particular elements. Y eta can be put here and x eta here. Okay, that we can do, and then we can change the sign of this anti-diagonal elements. Okay, minus x eta and minus y zeta. Okay, so through that we can come up with the inverse. So that is what I have written here, 1 upon determinant of A, that we can get it easily, and then we just change the position y eta x eta, and then we put the minus sign here. Okay, so that is the way in which we get the inverse. Now we want to equate zeta x and y eta, zeta x and y eta. So if you take the first element, you kind of get that relation very easily. Zeta x you have y eta. So what should be J now? So J should be this particular thing. Okay, so that is how we derive the expression for J matrix. Okay, so if we see this expression, equality expression, then we come up with J. So now if you see the option, I think you have two minus signs. So in the first option you have x eta y zeta minus y eta x zeta. So I think that will be the reverse. That's not the correct answer. So fourth one should be correct. X zeta y eta minus x eta y zeta. Yeah. So option number 4 should be the correct answer here. Yes. So let us see the last question for this tutorial session. Okay. Then we can take up the queries if there are any. Okay. So if two-dimensional space is in xy plane and the computational space is in zeta eta plane, which we have anyway discussed till now. Again, it's the question that the partial differential equation will in computational space be represented as which of the following. Okay, so this is, I think, can you write down in the chat box which equation is this? Dou u by dou x plus a into dou u by dou y. You might have studied this in the previous week contents, I think. Dou u by dou x plus a dou u by dou y.
Hello, yeah.
Yeah,
I'm audible.
yeah, you
I
are
have a
right.
doubt. Like I missed some of my assignments due to some circumstances. So is
Huh.
there an option that I can re-give them?
Assignments, I think you cannot give them. Maybe you can contact the NPTEL office, but I don't think.
Okay.
Yeah.
And if I have like below 320 marks in combined, so I won't get a certificate, right?
Okay. I don't know. I do not know the details of that. Maybe you can contact the IIT Madras, the no NPTEL office people. Okay.
Okay.
Okay. Okay. If you have any doubts in this, you can ask. Maybe. Okay.
Thank you.
Yeah. Yeah. So this is the last question. So basically, this is a 1D convection equation. Okay. So basically, if we convert this into the our computational space, what we can write it as? First, we can just convert this dou u by dou x using the chain rule expansion. Okay. Similarly, we can convert the dou u by dou y also using the just the chain rule expansion. Then we can just club these equations. In fact, I had written the Jacobian transformation also, but I don't think this is required in this particular question because everything is given quite straightforward. Like the equations are in terms of dou zeta by dou x only. Okay, zeta x terms are there. Okay, so you need not do this Jacobian transformation also. You need to write only this first line and this second line. Just add it. Okay, just using the chain rule, we can get the expression. Okay,
Yes.
so basically that's thing you can do. So this was the last question which I wanted to discuss today. So if you have any queries, you can write a mail to me also, or else you can ask now. If you don't have any queries, we can end them.
I got
And
your email ID.
just a second. Yeah, so this is my
Okay.
yeah. So with this, we kind of end all the tutorials for this particular course because this was, I think, the last week contents which were put up. Okay. So if you have any queries, you can write on the comment section in the YouTube video also. Basically, we will be uploading all the videos. I mean, we have already uploaded the 11 videos. This video will also be uploaded. Okay, so if there are any queries, maybe in the comment section also the queries can be written. So whenever I see it, I'll be able to answer it. So one of the main takeaway from this particular course is you should be able to write uh, numerical programs at least to solve Navier-Stokes equation. I mean, we don't expect to solve you to solve multi-phase flow or turbulence flow or something like that. At least on a simple structured grid, uh, taking simple problems like flow in channel, flow in some lid driven cavities, you should be able to write numerical programs to solve them. Okay, so that should be the main learning outcome of this course. That is my personal opinion. Okay, not only writing the quiz assignment and the exam, should always try to learn something which can be helpful in your career also. Okay, so with that I'll just stop the recording.